Hi. First of all, sorry that class was canceled today. I'm sure we're all very sad. I'm going to go ahead and briefly go over the notes for 9.1. All of these notes are on OneNote in Chapter 9. So, in the content library, I encourage you to review them on your own as well. And then also read the book section 9.1 and attempt the homework. And we will review this in the beginning of class tomorrow before moving on to 9.2. So we are now the second half of the semester going to be learning about sequences and series. So today we're going to start out with just some definitions and practice on what a sequence is. So a sequence is essentially just an infinite list of numbers. We're going to be, of course, focused on the list of numbers that have a specific pattern, but a sequence doesn't have to have a pattern. They're just a list. And we're not doing anything with the numbers. We are literally just listing them. A lot of times algebraically, we like to look for a pattern and then we can give a formula to the sequence. So in this case, and the notation is they use the letter S. Some books also use the letter A for a term in the sequence. And then the subscript tells you which place you are in the sequence. So S sub 1 here would be 1. S sub 4 would represent the fourth term, 1, 2, 3, the fourth term, which would be 16. And what they saw is, oh, there's a pattern here, and the nth term is n squared. So once I have the pattern, I don't need to list out every term in the sequence. If I wanted, for example, the 10th term, I know that that would be 10 squared or 100. So another example, in this case, they gave us the formula that S sub n is negative 1 to the n over n. Notice that negative 1 to the n is going to create a pattern where all the terms in my sequence alternate between positive and negative. So plugging in, this would be my first term. I plugged in 1 for n, second term, third term, fourth term, fifth term, right? If I wanted the sixth term, that would be negative 1 to the sixth over 6, which would be positive 1/6. Then the next term would be negative 1/7, right? This is one where we can sort of see the pattern. Another example going the other way, right? In the example we just did, they gave us the formula, we found the terms. Another kind of problem is they give you the pattern and you're looking for the pattern. These are usually the harder way to do it. It takes some practice. There's a little bit of trial and error. Things to look for is the pattern linear? Meaning, is there a constant rate of change? In which case your formula would look like some sort of an plus b, right? Like the equation of a line. Another thing to look for is, does it look like it's a power? In other words, is everything being squared, cubed, etc.? Or another kind of power where the base changes, do you have some sort of 2 to the n, 3 to the n, something like that? And sometimes, like in this case, you need to tweak a little bit. In this case, we're taking powers of 3, but we're not starting with n, we're starting with n minus 1. So the way they came up with that was they sort of looked at this pattern, 1, 3, 9, 27. This looks like it's 3 times 1, 3 times 3, 3 times 9, right? So this is 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, and 1 is 3 to the 0. So since we started with 0 and we're letting, in this case, our n, our counting numbers, we start with 1 and move forward, then our pattern here is going to be 3 to the n minus 1. And when you're coming up with your own formula, you can always sort of check, and sometimes you're not going to get the right answer on your first sort of thought. So check it and then, kind of edit it. So for example, if you thought this was 3 to the n, then you would check. And if n, I would use a table. If n is 1, you get 3, and you can see, oh, that's not right. I need to start at 1, and you would make some sort of adjustment. And then the next thing we're going to look at is sometimes we have sequences where you can't find a formula. So this happens to be the increasing digits for pi. So that's just an example of a sequence. Not every sequence is going to have a nice formula. We're going to skip this one. It's also sometimes useful to look at sequences with graphs. So since the sequence is just a list of numbers, it's not continuous. I'm not connecting the points. It's just that specific list of numbers. So here they're giving us a formula, and they want us to come up with a picture. So the first thing I would do is certainly figure out what those terms were. So kind of like a function, I'm going to make a table. N, which place I am in my sequence, is my input. the value of the term in the sequence is my output. So following the pattern, if n is 1, s sub n is 1 over 1 plus 1, or 1/2. When n is 2, s sub n is 2 over 2 plus 1, or 2/3. When n is 3, this is going to be 3/4. When n is 4, this is going to be 4/5. And if we look at all these numbers and we look for patterns, take a minute, pause the video even, and think about, what do you think the limit of all these s sub n's are? Meaning, as n gets bigger and bigger and bigger, are the numbers in this sequence approaching a number? So again, I encourage you to pause the video, try and think of the answer for yourself. Welcome back, hopefully. If you were looking at these numbers, we start out at 1/2, and then these fractions seem to be getting bigger and bigger and bigger and a little bit closer to 1, right? We can also look algebraically from the formula. The limit of n over n plus 1 would, of course, be 1. So the limit here looks like they're approaching 1. They'll never actually be 1, right? Even if n is 1,000,000, then my term would be 1,000,000 over 1,000,001, but they're going to get closer and closer to 1, which was why they decided that it has to be this choice C, right? Here I'm starting out at 1/2, and then my points keep getting closer and closer to 1, but never approach 1. So this is a nice visual way to see what the terms in my sequence might be doing. So just like for functions, we have the similar vocabulary. So if the terms in my sequence, like the example we just looked at, are approaching a specific number, kind of like for our infinite integrals, we say that the sequence converges. That doesn't mean that the value of the sequence will ever be that. It means that all the terms keep approaching that. So for example, the sequence we just had, we had 1/2, 2/3, 3/4, 4/5, all the way to n plus 1. So I would say the limit of the terms of these sequences is 1, right? These numbers each get closer and closer to 1. They'll never be 1, but as n gets bigger and bigger and bigger, I can get very, very close to 1. So that's what we call the limit of a sequence. And here's that notation that I was just referring to above. So we'd say the limit of the terms, the limit of the s sub n equals L, some number, then it converges. If the limit does not approach a number, then we would say that the sequence diverges. And again, a picture is very helpful for something like this. I can see that as I'm approaching infinity, these numbers spread out more and more and more and more, for example. And again, like I just mentioned, sequence diverges very much like a function if it doesn't approach a number. So it can diverge in different ways, just like with functions, it can oscillate. So here would be a sequence of numbers that's bouncing back and forth, getting further and further away from 0. Here's a sequence of numbers that looks like as n gets bigger, the terms in my sequence keep growing up and up to infinity. Both of those would be cases of a sequence that diverges. So calculating the limit of a sequence is very much like calculating the limit of a function, but our function is what we call discrete, meaning it's not continuous. It just has those points that represent the terms in my sequence. But I can use, if I have a formula, I can use all the strategies from calculus and pre-calculus that we use to find limits. Just like with our infinite integrals, we are going to have some patterns. So if I have a sequence of powers, x to the n, if my x is a number smaller than 1, the absolute value, then this sequence is going to approach 0, right? If I think about numbers less than 1, like let's say 1/2, as I keep raising them to powers, they get smaller and smaller and smaller, right? 1/2 squared is 1/4, 1/2 cubed is 1/8, 1/2 to the 4th is 1/16. So these ones get smaller and smaller towards 0. However, if the absolute value of x is a number bigger than 1, like let's say like 3, then as I keep raising them to higher and higher powers, it's just going to blow up to infinity. If my sequence is like a p series, like we looked at with our infinite integrals again, so like 1 over something, then we have the same pattern with those infinite integrals. If p is a number bigger than 0, that means my denominator keeps getting bigger and bigger and bigger, so my sequence will approach 0. And again, remember, n is the terms in the sequence, so n are always what we call the counting numbers. N are going to be numbers like 1, 2, 3, 4. Sometimes we'll have a sequence where we start counting the first term as a 0 term. Sometimes we might have a sequence where we say we're picking up this sequence starting with term 3, but the ends have to always be those counting numbers, whole, positive, non-negative numbers. So if p is bigger than 0 here, this is going to approach 0. If p is a negative number, that flips the fraction upside down, so then it's going to get bigger and bigger and bigger. So this is, again, an example of that here, which I did above as well. So again, scroll through the notes on your own and kind of read through all the examples. So here's a bunch of examples with what we were just talking about. The next vocabulary word we want to cover is bounded. A sequence is bounded if all of the terms are smaller than some number on the upper end and or larger than some number on the bottom end. So if all of my numbers in my sequence were stuck, if I looked at a number line and here was, 0 and here was 5, and I had some sort of pattern that no matter what happened, all of my numbers were stuck in between 0 and 5, we'd say that's bounded. If the terms in my sequence can keep going on and on to infinity, it is not bounded. So here's an example. This is one that we looked at before, the n over n plus 1. Every term is going to be bigger than 0. Again, remembering n's are the counting numbers. And also these terms will always be less than 1. So this would be an example of a sequence that's bounded. This begs the question, what's the connection between converging and bounded? So sequences can converge and not necessarily be bounded, because converge just means they approach a certain number. So it is possible for my sequence to have a limit, but not necessarily be bounded. And also the converse, just because a sequence is bounded does not necessarily mean it would be convergent. Usually bounded sequences that don't converge are sequences that alternate signs. So here's an example. This sequence is bounded. All my numbers are stuck in between 1 and negative 1. So it is bounded. The terms never leave the bounds of 1 and negative 1, but there's no limit because it keeps bouncing back and forth. So just being bounded is not enough to be convergent. We need another vocabulary word, and then we're going to get to how do we know if a sequence converges. Monotone. Mono, the prefix means one. So it kind of means your sequence is going in one direction. Monotone means your sequence has to always be increasing or always be decreasing. So if we put those ideas together, if a sequence is bounded and monotone, so it can't bounce back and forth, then it does have to be converging. So like that n over n plus 1 that we looked at earlier, which is bounded between 0 and 1. And this is always increasing. As n gets bigger, the terms keep getting bigger. So it's monotone, increasing. This would have to converge. So again, here's some examples, which I will let you hopefully read through in your own time. One other definition, recursive. A recursive definition is a definition where each term depends on the previous term. These formulas are actually usually easier to write. They're easier to observe, which was why we use them. They're not as convenient to work with, because if I want to find the third term, I need to know the second term. If I want to find the fourth term, I need the third term. So if I wanted the 100th term, I would need the 99th term. But to find the 99th term, I need the 98th term, and so on. But some sequences are so complicated that we can't have what we call an explicit formula. So we have to define it recursively. So we use this notation, sub n minus 1 means the term before it. So notice in a recursive definition, you have to be given sort of a starting point. So they tell us the first term is 4, and then every term is 2 times the previous term plus 1. So going on to the next term, s sub 4 would be 2 times the previous term, which is the third term, plus 1, and so on. And then we have an example here in our last 30 seconds before the video is done. A very famous sequence that has a recursive definition is the Fibonacci sequence. Most of us are familiar. In this case, you need the first 2 terms to be given to you, and then each next term is the sum of the 2 previous terms. This is a really hard formula to write a direct formula for. There is one. Notice how complicated it is. So that's why we like the recursive definition.